Hello everyone, what I want to do now is talk about the basics of Hilbert spaces, and from now on I'll more or less follow the book. Um, so how my presentation of Hilbert spaces is basically following the book. So I just want to remind you what an inner product space is. Well, it's just simply basically a vector space with an inner product. So it's a vector space X over the reals or complex numbers. So it's a vector space with a map, an inner product, taking x times x to either the reals or the complex numbers, depending on if x is a real vector space or a complex vector space. Satisfying the following three conditions. So for any x and y in big X, this almost commutes. Not quite. You need a complex conjugate here if we're dealing with a complex vector space. For a fixed z in the second variable, this map here is linear in the first variable. So if alpha and beta are scalars, x, y, and z are in X, big X, then this is just going to be alpha x z plus beta y z. And just playing around with 2 and 3, you can very easily see that if we go the other way around, if we fix the z in the first variable, then we almost get the same thing. We actually just need to get, it's a complex conjugate here. So we get alpha bar z x plus beta bar. And if you have any doubts, just check this for homework. Okay, and last but not least, well, we want this, of course, to define an inner product in the obvious way, so we have to assume that x inner product x is bigger or equal to 0. And the only way you get this to be 0 is if x equals 0. Okay, so given an inner product space, we can find the norm in the obvious way. We'll take inner product x with itself raised to the 1/2 power. Okay, so a Hilbert space is just, by definition, a complete inner product space. And if you're wondering on my YouTube channel who that person is with the hat and the beard, that is David Hilbert. Okay. Yeah, and if you want to know more about him, there's not a lack of historical references. Just Google him and you can learn a lot about him. Okay, so I want to prove that actually this defines a norm. Okay. That's pretty easy. So to do that, first we need the following lemma, which is, as you probably know, called Cauchy-Schwarz, and this will be for homework. So in any inner product space whatsoever, real or complex, we have the following: the absolute value, or the modulus of x inner product y, is less than or equal to the norm of x norm of y. And so by this I mean, it's maybe, by this I mean x to the 1/2 times y to the 1/2. We're just, when I write this here, even though I don't know it's a norm yet, when I write this, I mean x to the 1/2. Okay. All right, so, right, so let's prove that we actually have a norm. So everything but the fact that the triangle inequality is true is pretty trivial. It really just follows from 2 and 3. So let's prove that the triangle inequality is true. Okay. And we really just have to use the definition. So by definition, this is going to be x plus y, inner product x plus y, and it's fairly obviously much easier to work with norm squareds because they get rid of square roots. Okay, so now just use property 2. This is going to be x plus x y plus y x plus y y. And of course, this here is going to be xy conjugate. Okay, so this is just going to be equal to, well, of course, it's just xy if it's a real inner product space. Yeah, so any complex number plus its complex conjugate is just going to be 2 times the real part. So this is just very simply, and this alone is quite useful. So I will isolate it. So this is my norm x squared plus 2 times the real part of x y plus norm of y squared. So let me put this in blue here because I'll use this for the next result I prove. So let's continue on with this. Well, I always have that a real number is less than or equal to its absolute value. So this is absolutely trivially less than or equal to norm x squared. And again, we don't know it's a norm yet. We're proving that, so I really probably shouldn't call it norm squared, but whatever. Plus 2 absolute value of x, y, inner product. Again, I'm using the fact that the real part is less than or equal to the absolute value. Plus y squared norm. Use Cauchy-Schwarz. I'm sure this is a very familiar proof. And you get exactly norm x plus norm y squared when you do this. So now take a square root of both sides, and that proves the triangle inequality, and that proves that we have a norm. Again, the other properties are pretty much trivial to check. Okay, so a corollary of the proof that I just presented of the triangle inequality is what's called the parallelogram law. And yeah, I think it's worthwhile to draw a picture, particularly if you get into maybe deeper aspects of Hilbert spaces. If you end up doing applied, machine learning or something more applied, you sometimes have to, think very geometrically about Hilbert spaces. So, it's often easy to prove things, but unless you kind of know what's the geometric reasoning or the kind of geometric meaning of something is, it's not, especially when you start doing research, it might not be very, it might not be clear at all why what you're proving is true. All right, so what's the parallelogram law? Well, the parallelogram law says in any inner product space whatsoever, I add these two quantities together, and I get 2 times the norm of x squared plus 2 times the norm of y squared. Right, so the picture is, let me see if I can move this up a bit. No. Anyway, that's fine. Yeah, so I want to draw a nice big picture here. So, yeah, so let's just draw a parallelogram. Let's say this is y, this is x. Right, or let's just draw these 2 vectors here. Okay, so basically, here I have, better. Let me draw a carbon copy of x here. Might not be exact, but. And let me draw a carbon copy of y here. Okay, so, right, if we add x and y, I just move x to the tip of y, I'm going to get x, and I get x plus y right here. Bit hard to draw a straight line. Anyway, don't want to waste too much time here. This looks a little better. Okay, well, if you take minus y, which will just basically be this vector here, but pointing down, and if you take x minus y, or rather, sorry, minus y is just this vector here pointing down, add to x, you'll get, sorry, this is x plus y. I'll do it in, I guess, blue here. Yeah, this is going to be x minus y. So really what, for the inner product space R2 with the usual inner product, the parallelogram law is just this, this basic fact about parallelograms and in the plane, that if I take a parallelogram like this, then yeah, so you take the length of the diagonal squared, that's going to be equal to 2 times the length of the base times 2 times the length of the, or 2 times the sum of the length of the bases. The base being x, the length of the base being x, and the length of y. The length of one base being the length of x, the length of the other base being the length of y. Okay, and so this is saying that, this kind of happens in any inner product space. And the proof is, it's very simple. Yeah, I'll be able to, should be able to fit it here. As we'll see, this is extremely useful. Yeah, so we use what I put in blue here, and I'm going to do it twice. One with y here, and one with y replaced with minus y. So from what I circled in the blue moments ago, well, literally, what I have circled in the blue is going to be this here. Plus 2 times the real part, x, y, plus the length of y squared. Okay, so now if well, let's say I replace y with minus y. So let me get rid of all this here because I don't need it. I want to avoid confusion. Right, so what happens if I do that? Well, here, if I take a minus y, I can pull the minus out, so this becomes a minus. Minus the norm of y is the norm of y. Okay. So I should say, actually, this picture here doesn't help us prove it necessarily. But it says, well, it basically tells you what's the meaning of the parallelogram law, and it tells you why it's called the parallelogram law. It's in the plane, it's a theorem about, it's a basic geometry theorem about lengths of bases and diagonals for parallelograms. Yeah, and definitely basic geometry in the plane often gives you intuition on what should be true for inner product spaces, and more generally, just normed vector spaces. Okay, now all you literally have to do is add these two up. These cancel out. So that you get 2 norm x squared plus 2 norm y squared. And that's basically the proof. Not a whole lot to that. All right. Right. So, yeah, make sure we're all on the same page here. Some very simple examples of particularly Hilbert spaces. Well, of course, Cn with the inner product for x and y and Cn, usual inner product, or Rn. Just multiply these two complex numbers together. Maybe I'll do z and w. It's more conventional for complex numbers, but whatever. So here z is the n tuple of complex numbers z1 through zn, and w is the n tuple of complex numbers w1 through wn. Of course, L2 has a natural inner product. Just integrate over the real line, or really any L2 of any measure space. Or here it could be, you could have any interval here, whatever. The Bergman space, well, it has kind of the obvious inner product too. Remember, we defined the Bergman space, I believe, a few videos ago. Yeah, so this inner product is just, oops, just integrate over the unit disk, ordinary Riemann integral, actually. All right, so I actually want to, let's see. Yeah, so I want to state a corollary of this right here, actually. It's something to remember here. Basically, this is called the Pythagorean theorem. So if this inner product is 0, well, we can see right from here, so let's go back to making it a plus. Well, if this is 0, then this is just the usual Pythagorean theorem. Norm of x plus y squared is norm of x squared plus norm of y squared. Okay. And we say x and y are perpendicular to each other if x inner product y is 0. Often we write x, bar, or x, this perpendicular symbol, y, to denote this is true. Okay? So again, this is called the Pythagorean theorem. It follows exactly, as a trivial corollary from what I have here. Okay, and if this is true, yeah, we call x and y perpendicular or orthogonal. I don't know exactly the literal meaning of orthogonal. I think it's Greek, but or Latin, whatever. But anyway, okay, right. So yeah, this leads us to more definitions. So if I have a inner product space X, let's say I have a subset A of my inner product space X. So I'm going to define the orthogonal complement of A, denoted by A with this orthogonal perpendicular symbol here, to be, instead of all y and x, well, that's orthogonal to everything in A. Yeah, so it's basically, in some intuitive sense, perpendicular to A. So an easy example is the following. Well, let's look at the following. In R2, just a set of all x 0 such that x is an R2. Well, that fairly trivially is going to be, so this is basically the x-axis, right? So yeah, let me do this here. Now let me do this in red to emphasize something. Yeah, so this is going to be the set of all 0 y. Sorry, this should be x's in the real numbers. Right, so just kind of right, so A is just, Well, A is just the set of all, if we think of vectors in the plane with, the emanating from the origin, then A is, of course, just all vectors sitting on the x-axis. Then A perp, sorry, I should say perpendicular, it's not a symbol here. Yeah, so if this is A here, then A perp is just going to be well, basically all vectors, basically the y-axis. Right, so a fairly easy homework that's quite useful is the following. For any subspace, any subset of a inner product space, it actually doesn't need to be a subspace. Well, the only thing that's possibly in okay, so I want to mention something that's quite useful, and I'll leave this for homework, is that the only thing that's possibly in a subset of an inner product space and its orthogonal complement is 0. So this is just 0 if 0 is an A. Well, so maybe it's easier to write. It's going to be 0 intersect A. So what this means is if 0 is not an A, then there is nothing that's both an A and the orthogonal complement. If 0 is an A, then then this is going to be equal to 0. Also, the orthogonal complement of A is it's a closed subspace of my inner product space X, regardless of anything whatsoever about A. It's always going to be a closed subspace. Okay, so we have a definition that's quite useful. And then I'll get to proving a very important theorem. So we say that a subset of X is pairwise orthogonal if whenever we have X not equal to Y and X and Y and A, then these are orthogonal. Okay. Right, so example, yeah, so this is an example of a pairwise orthogonal set in L2. Take any two different elements here, just compute their inner product. We did this before, it's very trivial. We get 0. Okay. Right, and something I'll use without really further say, if I have a sequence, and here big N can be infinity. So if these are pairwise orthogonal, then we have by induction and basically continuity of norm, j equals 1 to infinity. Well, let's say n is just, let's not use n is infinity. Let's just say n is a natural number. So by an easy induction, this is going to be equal to, well, just use Pythagorean's theorem, basically, an induction. The norm squared of the sum is the sum of the norm squared. All right, so I want to finish this video off with the very foundational, important result in the theory of Hilbert spaces, both pure and applied math, which is the nearest point theorem. So first, I need a definition. So we say that a subset let's call it capital K of a norm of a vector space, doesn't have to be normed, is convex if x and y in K and t between 0 and 1 implies that tx plus 1 minus t y is nk. So if x is R2 or R3, then we have a very natural pictorial interpretation of what I'm circling in green for all t, and that is it's just the literal line segment connecting x and y. In general, what I circled here, we call the line segment connecting x and y. So all convexity is saying is that K is convex if for any x and y in K, the line segment connecting x and y is also in K. So for example, let's draw something like this here. So let's say, so let's say K is this geometric object, let's say x is R2. And let's say K is inside this object here and including the perimeter. Okay, so you can see, pick any x and y here, including possibly in on the perimeter, boundary, whatever. So we take the line segment connecting any x and y. Well, we still stay in K as long as x and y are in K. So this is convex. On the other hand, let's look at something like this here. Right, so let's look at, say, something like this here, which is pretty horribly not convex. So I actually want these two line segments to be the same length. Explain why in a second. So maybe just make it a little longer. Anyway. Right, so let's take just simply something like here x and here y. Take the line segment connecting x and y, you can see, I mean, it's actually, except for the endpoints, it's actually never in K. So this is miserably not convex. And here, K, again, is this geometric object and everything inside of it, including the perimeter. Okay, so the nearest point theorem is as follows. Nearest point theorem. Let K be closed and convex. So let's say H is a Hilbert space and K is closed and convex subset of my Hilbert space. So given any H and big H, there exists a unique K0 in big K. Where the distance between H and K0 gives me the distance between H and K, the set K, which by definition is, well, the obvious thing, just the infimum of all possible distances between H and stuff in K. So in other words, what we're basically saying is that this is not an infimum, it's actually a minimum, and that there's a unique element in K that realizes the minimum. Okay. So for example, let's just do a pictorial example. So let's say here is H. Okay, you can basically pictorially see that if I just, kind of drop down to here, then this is going to be my K0. I mean, take any other K. Let's do a K here. The distance between H and K is going to be larger. Okay, so this K0 is a unique element in big K, where the distance between H and big K is given by the distance between H and this element in big K, which we call K0. Okay, so actually, such a K0 will always exist, convex or not, as long as H is finite dimensional. But when we deal with infinite dimensional inner product spaces that are complete, we do need convex. Talk about that later. But regardless of finite dimensional or not, you absolutely need convexity for uniqueness. So very easy example would be, let's take, one second. Right, so let's actually just this again. Let's say that's a straight line. Let's say these have the same length. Let's say this is, yeah, so let's take H to be right here, the middle, the midpoint. Actually, let me not do that. Let's say H is, let me make this a little bit different. Sorry about that. Right, so let's say we have something like this here. So that. Okay, so let's take let's say I have the midpoint between the line segment containing these 2 points. Let's say right here. Okay. So let's say this is my H here. So then graphically, it's at least reasonable that if H is a midpoint here, then both these distances are going to give me the minimum distance between H and anything else in big K, which means that there is not a unique element in big K that gives me this distance. There's 2 of them here. So without uniqueness, sorry, without convexity, you don't necessarily have uniqueness. Okay, so it's a really nice little proof. Okay, so by definition of an infimum, in some sense, at least the starting point of the proof is fairly obvious. We can pick xn and k. And this is just, again, the definition of an infimum, where this limit here, sorry, h minus let's call this here d for distance. Yeah, so pick a sequence where this limit here is given by d. If there's any doubts, then you absolutely should prove this literally just definition of an infimum. Okay. Okay, so by parallelogram law, so instead of x and y, we're actually going to replace x and y with x over 2 and y over 2. If we do that, we get the following. X plus y over 2 norm squared plus x minus y over 2 norm squared is going to be given by 1/2 norm x squared plus norm y squared. Or in other words, just bringing the x plus y over 2 norm squared to the right-hand side, we get x minus y over 2 in norm is 1/2 norm x squared plus norm y squared. So I should say what I want to do is I want to prove that xn is Cauchy, and because we're in a Hilbert space, that'll mean the limit exists. And the way we're going to do it is using this consequence of the parallelogram law in conjunction with convexity. Okay, so, well, let's say x is h minus xm and y is h minus xn. Okay, so this says that, well, just plug in x and y, we get xn minus xm over 2 and norm squared is going to be equal to 1/2. So actually the book assumes h is 0 and then then does a general argument to reduce to that case. I think it's easier just to not really assume, just to use h in general. I don't think it helps much to assume h is 0. It makes it a little bit easy. No, it doesn't even make it easier. It makes notation a little simpler. But anyway. Right, plus, well, if you plug in x plus y over 2, you're going to get h minus xm plus xn over 2 norm squared. So by convexity, you'll notice that this is actually the midpoint between, well, I mean, if xm and xn are in R2 or R3, this would pictorially be the midpoint. But in general, from convexity, setting t is 1/2 and using the fact that this is a subsequence, this is a sequence of elements in big K, this is certainly in big K. Okay. Well, h minus something in K is, I'm sorry, this should be a minus. Super important. Do not want a plus. Sorry about that. Right, so this quantity that I'm circling with my cursor is bigger or equal to the infimum of h minus K, where K is in big K. So minus is less than or equal to the infimum. When we said D, we just said, well, let's call the infimum D. Okay, so this is less than or equal to, just, by definition, the infimum is a lower bound, 1/2 h minus xm squared plus h minus xn minus d squared. Again, remembering d is this infimum, so this whole thing here is bigger or equal to this whole thing squared is bigger or equal to the infimum squared, hence minus is less than the infimum squared. Okay, but xm minus h and xn minus h converges to d in norm as m and n go to infinity. So this converges to 1/2 d squared plus d squared minus d squared equals 0 as n and m go to infinity. That implies that xn Cauchy. So let's say let's call this K0, and because big K is closed, K0 is in big K. So I should make clear that Certainly K0 might not be in the set if it's not closed. So for example, let's say right, so let's say K is the inside here. Yeah, let's say big K is the inside here, but just the interior without this perimeter here. So yeah, you get the point here. So everything with this picture is fine, but just K0 is not in big K because K0, there is basically, a unique K0 in the closure of big K where the infimum of distances between H and stuff in big K is realized by H minus something in the closure, but it does not live in the actual set K because, well, K0 is on this perimeter here. It's not in big K. K is just the interior of this object here. Okay. Right. So definitely for it to be in K0, we need closed. Okay. So now by continuity of norms, well, K0 converges to, or Xn converges to K0, so H minus Xn certainly converges to H minus K0. Kind of trivial. And remember, the starting point was how we even picked Xn is that this converges to D. Okay. So the existence of K0 is proven. So now we just have to prove uniqueness. Okay. Sorry. And uniqueness is fairly straightforward. Let's just assume we have two elements in K. Let's call it K and K prime, where the distance between H and both of these give me D. Okay, so by star, I'll go back to it in a second, with X equals H minus K and Y is H minus K prime, we have, so yeah, we're star. So plug in H minus K and H minus K prime for X and Y respectively. We get K minus K prime. So I should say, what are we doing? We're going to prove that this here equals 0, and hence K is K prime. So this is given by 1/2 X norm of X squared, H minus K plus norm of Y squared, minus, again, just plug in, you'll see it's going to be H minus K plus K prime over 2 squared. And again, this is, I forget what color I used, but whatever. This whole thing here is certainly in K. Just setting T to be 2. Okay. Right. Well, both of these are equal to d. So let me erase both of these and replace it with d. So this is d squared and this is d squared. Okay. But again, this whole thing here is in big K, so this is h minus something in K. That's bigger or equal to the infimum of all distances h minus stuff in K for all stuff in K. Minus it makes it less than or equal to the infimum. So it's less than or equal to 1/2 d squared plus d squared minus d squared equals 0. Well, how on earth can we have the norm of k minus k prime over 2 squared being less than or equal to 0? Well, that implies norm of k minus k prime is 0. Implies that k is k prime. All right, so in the next video, we'll talk about orthogonal projections. And then we'll start talking about linear functionals and prove the Riesz representation theorem. I'll try to go a little bit quick with all this. And as always, anyone, please tell me if I'm going too slow. You know, I really do want people to, you know, I always think a review, especially with homework, is good. So, you know, if it's beneficial for me to go this slow, I'll be happy to go this slow, but otherwise I'd be happy to speed things up. All right, take care. Bye-bye.